All right, now that we've got the bare minimum basics working, we're going to start to refine things. So first of all, there's a little bit of a problem with this pixel shader, and that is it's not respecting some of our material data here. So we're not actually, we have to, when we take the diffuse and the ambient light components to determine the final color, we actually have to multiply by the material color, and we're not doing that. So this is a Hadamard multiplication here. And we should be multiplying this material color in, but we weren't, so we added that in there. And that's going to allow the material color to be reflected. So a little bit of a fix there. The next thing is a bit of a refinement. So now what we would like to do is, instead of hard coding those material values into the shader, the light values and the material values, we want to put those parameters into constant buffers. So we're going to put them all in the light constant buffer to start with. And then for our point light, and then for our point light object, we're going to add more stuff to the data structure on the CPU side. And for the data that the object is managing, instead of a single float 3, it's now going to manage the entire data of this structure. So now it's adding a lot more, it's managing a lot more data. So the reset function is going to be more complicated. And we're just going to call reset from the constructor to initialize all that stuff. The control window now has to refer to cbdata.position.xyz. And down here, what are we doing here? For the draw and the update, we're using cbdata instead of using the position stuff. But yeah, it's the same sort of deal, not that complicated, except for one problem. That is, it doesn't work. So if you run it, you get a exception here. It says that the size of the constant buffer at slot 0, the pixel shader, is too small. 64 bytes provided, 80 bytes at least expected. Now, it would be possible to use the graphics debugger to inspect the constant buffer contents at the shader side and figure out what's going on here. But to make a long story short, we define our constant buffer here. We define it as float 3. I can't say that. But this will pack them all together. But the thing is what the GPU side is expecting. If we look at our shader here, so it's expecting these float 3s to all be aligned at 16 byte boundaries. So it expects to have float, 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 padding, float, 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 padding, float, 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 padding. But what we're giving it is all these float 3s packed together with no padding in between. So the solution in the next commit is very simple. We just, we could put padding variables in between here, or I could just use align as 16 for all of these. And if I declare it with alignment of 16 bytes, the compiler will add the padding in there for me, which is nice. So if I run this now, it works exactly as before. And now you can see that the material color is being used, and the blocks, they look a little blue because that's what the color I was using, was a little bit of a blue in there. So the next commit here, lots of light params. All I do is I add the ability to now manipulate all those different light parameters from our window. You can see now we've got lots more options here. I can change the material color to maybe be something more like a red. You can see here now the color of our objects is changing. I think it was more of a blue there, to be honest. And we could also change the parameters for the fall off. So we could make the quadratic fall off a lot bigger, and that would have a pretty profound impact on our object lighting. Or the linear fall off. You can see that working. Or the constant, which just does a general attenuation irregardless of distance, basically. But yeah, so more parameters for you to mess around with and explore all the different variations. Now, what we're doing here, basically including the material color as part of the lighting parameters, isn't really a good idea, because you have a single light, let's say, in the scene, but you might have many objects. Do you really want all those objects to be forced to have the same material color, or would you rather to be able to set their material color separately? Material color is a property of the object, not of the light. So we want to pull this out and put it into our drawables. So that's what this commit here is about, multiple slots, and we'll see what that means in a second. But to begin with, let's take a look at our Phong pixel shader. So what we've done is we've actually separated this into two different constant buffers, because one of these constant buffers is going to be set per frame for the light, and the other one is going to be set per object for each object that we render. So we need two independent constant buffers. So that means that this one is going to be defaulted to slot 0, and this one is going to be defaulted to slot 1. Only our current constant buffer implementation always binds to slot 0, which obviously isn't going to be very scalable. So we need to change that. So what we do is in constant buffers, we actually add another piece of member data called the slot. And that's where we're going to hold information about the slot, and we use that slot data. It's now protected, and we use that in the pixel constant buffer and in the vertex constant buffer. When we call bind, we're now going to bind it to that stored slot instead of binding it to 0 every time. Now, so the constructors for the vertex constant buffer and the pixel constant buffer, they'll have to take in a slot. So that means we have to change transform cbuff to also take in a slot, but we can default that one to 0. And in here, we use that slot to construct the vertex constant buffer. So now we have the ability to set which slot a constant buffer will be binding to. And so then in box dot, what do we do in box.h? We add member data to store, or we add a parameter that can be passed in for the material color. And then in box.cpp, what we do is we create the material constant buffer that stores a color, and we set that to the color that was passed into the constructor, and then we add that bind to our drawable, and we tell it to bind this one to slot 1. And then in app.cpp, we create a new distribution for color, and we make sure we construct a material color from this distribution randomly, and we pass that in to the constructor when we are going in our factory for making drawables. And if you run that, now you see we've got our drawables, and they all have different colors, and they're all being dynamically lit. It's a beautiful time to be alive is what it is. I hope you will agree with me. So now we got our dynamic lighting, diffuse lighting all set up nicely, all organized between the object and the light. Now what I want to do is maybe add a little bit of specular highlights to the story. So we got this one here. Problem with specular, you can already tell that there's going to be a bug in here. Deleted sheet, I don't know why, I just did it because I didn't need it, I guess. But more importantly, let's look at the changes we've made to the Phong pixel shader. All right, so for the object, we've added additional properties for the material, specular intensity and specular power. These two together will control the shininess of each object individually. It's not a property of the light, it's a property of the object. And down here, I've added a bunch of math for specular highlighting, and this is based basically on what we did in 3D fundamentals again. Basically what we do is we calculate the reflection of the vector that is going from the light to the pixel. We reflect that on the surface of that pixel using that normal of the pixel. And then we compare that reflection to the vector from our camera to the pixel to see how much it's pointing in the direction of the camera. And we do that using a dot product with the power. And that gives us our specular component. And then we just add that component together with the diffuse in the ambient, and that gives us our total light power for that pixel. Multiply that by the material color, and there you go. Some models will allow you to have, separate color for specular and diffuse on the material, but I don't mind. I'm just going to keep it the same for this one. Keep things a little bit simple. And then in box CPP, we are just going to update the material constant buffer. We're going to add specular intensity and specular power, and we're just going to set them to constant values for right now. Now, when you run this code, you're going to see that the specular stuff is kind of funky. You're going to get specular reflections on surfaces that aren't really pointing in the right direction for them to be reflecting. And the reason for that is because, well, the code that I'm using here, it was taken from 3D fundamentals, but it was actually assuming that these coordinates were relative to the camera. And they're just right now, they're just in world position. They're not relative to the camera. So in order to make this work, we have to make the coordinates relative to the camera, or we have to change this algorithm and make it a little more complicated. So what I decided to do was to just work in the camera's frame of reference. So what you do for that is, well, let's look at the Phong Vertex shader here. So what we're going to do is, instead of having a model and a model view projection matrix, we have model view and model view projection. And now the world position is actually going to be, I should have maybe renamed this, but it's actually going to be the position relative to the camera. So it should really be camera position. Well, too late now. So we use the model view to transform the world position and the normal. And then in the Phong shader here, instead of using the direction to the light, I'm using the vector to the light. So this direction is the normalized vector to the light. So I'm using the non-normalized, which is apparently the proper one to use. Again, for all those nitty-gritty details, you should really go back to 3D fundamentals. But a little bit of fix up on the algorithm here. Also here, I changed from using the reflected vector to the negative of the reflected vector. So a bit of changes around here. And now, because we're using different set of transformation matrix, here, instead of using model and model view projection, we're now using model view and model view projection. So if we do that now in our Phong pixel shader here, now this world position and this normal are relative to the camera. But the problem is that the light position was still in absolute world coordinates, not relative to the camera. So it doesn't match up with this position here. So what we have to do, and that's what this commit is all about, is we go into point light, bind, has to take in the view matrix from the camera. So when we bind the point light, we have to take in the camera matrix. I don't really like having a little bit of coupling between those two, but it's the way we had to go. It was the simplest option for me at the time, is basically what it boils down to. So now when we bind, we make a copy of the data from our light, and then from that data, we load the position of the light. We transform that position with the view matrix, and we store it back into the data copy. And then we update the constant buffer with that data copy. So now the constant buffer that contains the light information, the light position, is now relative to the camera, which matches the normal and the position of the pixel. So now all three are relative to the camera. And if we do that, now we can see that we are getting proper specular highlighting. You can see it happening here. If you pay close attention to these surfaces around here, little glints of specular highlighting. And it's very pretty. It's very nice. Now, one thing that I missed out here, and I think this was, again, a product of me basically copy and pasting from 3D fundamentals, was that I was not attenuating the specular component by the distance. And I should be doing that, I believe. I believe attenuation of this is also necessary. The reason why I wasn't doing it in 3D fundamentals is I believe I was using a directional light at that time. So I did not attenuate it when I created that code. But anyways, attenuate that, so that'll make things that are farther away from the light source have a weaker specular reflection on them. Now, the next thing I did is a little bit of organization in anticipation of creating different drawables to add to our system besides boxes. So in box, you have a lot of boilerplate, like these variables. They're common to basically all the drawables. They all need to have these kind of position data. So what I did was I pulled them out of the box and I put them in a new object called the test object. And so it has, you know, those positions. It has a constructor that initializes them. It has the update function. It has the transformation function. And then in box.h, we just inherit from test object, which inherits from drawable base. So now we have this additional layer of inheritance that allows us to factor out a lot of the boilerplate that doesn't change between any of our drawables. And it's just noise that we want to get out of our content classes. So we do that, and then we begin by trying to add a new object, a new drawable, a cylinder. Now the way the cylinder works, the model, it's based on the prism model with a lot of tessellation. We'll make it a cylinder. I've explained that already. But to generate cylinder with independent caps, so it's going to be flat shading on the top and the bottom, but smooth shading around the curve of the cylinder. We need a lot of code to generate that geometry in those normals. So I wrote this, and I wasn't not happy, but I did it, and yeah, it's done. And then cylinder.h, you just inherit from test object. You notice that the h files now have become very small. And cylinder.cpp, we call the constructor of test object. And then down here, we create the geometry, bind the vertex buffer, shaders, all that happy horse crap. We're using, for the color, we're using a lookup table together with dynamic shading. You'll see that working. And yeah, that's basically it. What did I change in drawable? Added type info. This was probably added this in here. I removed it. It's probably some kind of debugging stuff I was doing, and I just removed this because it was added in before. It doesn't matter. It's not important. That is not super important. We had cylinder in here. We added to the factory. And that's about it. Indexed Phong. Oh yeah. Well, obviously we needed a new pixel shader. We could reuse the Vertex shader, but the pixel shader has to be different because now the constant buffer for the material isn't taking in a single color. It's taking in a table of colors, a lookup table. And then when we're going to determine the material color, we have to use the primitive ID to look up into that table. Not super complicated except for the geometry generation here, which was a huge pain in the dick, I'm not going to lie. But when we run it, we find out the lighting on our cylinders is completely messed up. It's just terrible. Doesn't work. Also, the geometry on them seems to be messed up. So we've got problems. We've got some problems. Now, one thing that you should probably be aware of is that when you're using the primitive ID, and then you go in with your debugger, your graphics debugger, you're going to get a little notice here. This draw call uses system value semantics that interfere with pixel history computation. So you can't debug your shaders properly when you have these this ID, texture ID, not texture ID, primitive ID, triangle ID, or whatever you want. It's just not going to work. So what I did is I temporarily removed the primitive ID so that it would be possible for me to debug the shader. So what I did was I removed that primitive ID, and that allowed me to debug the things, and I found out the problems. And I'm not going to go over the problems here because they're kind of annoying. Well, this one is. The first problem was some problems with my geometry. And again, that's just going to be, that would like take an hour to go over maybe, to talk about all this dumb geometry generation. And it's not super important because most of your geometry is going to be loaded from, pre-built files instead. You're not going to be generally generating geometric primitive shapes using mathematics yourself. But if you're really interested in, I do some of this in 3D Fundamentals, so you can look at that. But I went through and I debugged my geometry. I made it a little better. It's still not perfect here, but it's better. And then here, I do better fixing up. So there are two problems. One of them was the geometry. The other problem was the alignment of the constant buffer data. And this is something you really have to be careful with when you're writing shaders. This constant buffer alignment stuff between the CPU and the GPU is really annoying. And there's really no clean way of doing it. You just got to be very, very, very careful. So, what do I mean? Well, what we had before was I put these guys here, these float 3A. These are supposed to be aligned floats. So what we should get here is we should get float, float, float. This is in CPU, by the way. Float, 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 and then padding. Float, 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 padding. Float, 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 padding, and padding at the end here. And then these two guys, this one will be aligned at 16, and this one will be coming right after this one. That's what we expect, and that is what we get. Now, here is what the GPU expects. So let's look at what we had on the pixel shader side. So we have material float 3, 6 of them. So you should get float, 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 padding, float, 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 padding, blah, 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 blah. And at the very last one, you're going to get float, 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 no padding, and it'll immediately put this guy right after the last float of this one without any padding, because a single float doesn't need to be aligned, so we can stick it right in after this float 3 without any padding. Only what we were doing here by making this aligned automatically adds padding, so this guy does not come immediately after this one here. There's a one padding float and then it comes in. So you see that there's that misalignment between the CPU side and the GPU side. And the way I chose to fix it was add some padding in, this time on the GPU side. Force it to add some padding in here that we don't use. And this way, these two will come at the places where they're expected. The alternative to that I could see is manually padding all of these. So putting padding behind this one, this one, this one, this one, this one, and not putting padding behind this one on the CPU side. But that seemed more cancerous to me than simply adding in one padding on the GPU side. So that's what I chose to do. But again, it's annoying to try to figure out. But if you use the graphics debugger, you can inspect the contents of the constant buffer, and you can see sort of what's going on, especially if you choose very striking values for all these constants here. You can see what's happening in the memory on the GPU side, and you can see, oh my God, this thing where I thought there was going to be padding, there was no padding. But anyways, so yeah, we changed that, and I just changed this one to match what I was doing over there a little bit. So I removed this align as here, add a little bit of extra padding at the end, but you get the idea. And here's what it looks like with our cylinder all fixed up. Very pretty. You can see our specular highlighting is working on the cylinder as well, on those edges there. And index coloring, very nice, very stripy. There's one thing I wanted to show you, but I kind of forgot, and that is when I was debugging the... There's one thing I wanted to show you guys and I kind of forgot, but I'm going to show you right now, is when I was debugging the generation of the geometry for the cylinder. I used a little bit of a different tool that I haven't shown off yet with the debugger, geometry debugger. So here's what it looks like. It's pretty horrific, if you ask me. But if I go press print screen, capture a frame there, and I can open that up now. What we can do is we can actually inspect the geometry of these objects and maybe get a little insight into geometric problems, not just shader problems, but also problems with the geometry. So if I look at this, you can see here in the pipeline stages, a bunch of information is being shown up here. So the input assembler, and we can see our model before it hit the Vertex shader, after it hits the Vertex shader, what it sort of looks like. And then you can see how it is merged into the frame buffer here. But what we really want to see is this one here. This is our original model as it's hitting our pipeline. And what you can do with this, I don't have very much space because I'm recording 720, you know how it is. But we can actually rotate around here and inspect our model at our leisure for each model that hits our pipeline. And that's a nice little feature. You can sort of get a better idea of what's going on if you're having geometric problems. And you can see here there are different drawing modes. So here's a shaded drawing mode, but there's also overdraw. And there is another one called wireframe. You can see it as a wireframe. Very nice. There's also, this is very, very useful. You can show vertex normals. If I select it, now you can see all the normals on the vertices. And normals are often a big problem that you have with models, incorrect normals. So being able to diagnose those, also very nice. And I think this is a good place to call it for part 2. We got a lot accomplished. We separated the material and the light properties into separate constant buffers. We implemented shininess. We got a good start on adding other drawables back into our scene, and we saw yet another use of the all-powerful graphics debugger. Stay tuned for part 3, the conclusion, where we're going to complete our scene by adding the other drawables, including texture plus Phong shading, back into the system. And we're also going to have a little bit of fun with ImGUI by allowing us to change the properties of individual boxes at runtime. Until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button, helps a lot. And I will see you soon with some more Hardware 3D.